Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about Hera ESA mission. So let's dive deep into it. So before you understand Hera, you have to understand what the hell was DART, because this is the aftermath of DART mission. Now, DART mission was the double asteroid redirect test. Basically, you have to understand there are some huge ass asteroid. Now, benefit of them, they are huge, they are very easy to detect, and they're very easy to predict what's gonna happen and all that. So that's the cool part. But here's the, this is what we call city killer class. These are tiny puppy. They are not like so small that they will burn up in the atmosphere, but they are not so big that we have giant radar return, we have giant pixel capture area in a telescopes. You can easily see it. Tada! So this is a very dark area where they are a very big danger, and we have no way of actually understanding. So somebody came up with the idea. It's like, what if we try to test out a hypothesis? Is like, because here's the asteroid impacts are absolute, they're gonna happen. Let that be very clear. It's not a question of if, it's a question of when. And we already had few close calls, like really close call, like one of the really close call where you can see dash cam video. We were so lucky that it entered in a shallow angle. If it had entered like this, yeah, bye bye a giant area in Russia. Like it would have poofed that area. We are just lucky that it entered in a very shallow angle. That happened. There is video camera footage of it, and I mean modern video camera kind of footage. So question is not if, question is when. So question becomes, what are your protocols against it? Like how we build a tsunami wall, or how we have buoys all around the sea to figure out and give us early warning. In that case, we need something for asteroid. So this puppy was that brainchild of that idea. So this was launched on 24 November 2021 on Falcon 9, and this puppy kaboomed basically dimorphous on 26 September 2022. Now be mindful, because this is so small, it barely has any radar return or any sort of optical fingerprint, because you can barely see it, barely. So as you can see, like this is the best we got. So how would you know that you did something to it? Well, very, very simple. It has a moonlet, so to say. That moonlet is orbiting it. So Deimos and Dimorphos. Dimorphos, if we attack it from one angle and we can dump enough kinetic energy into this puppy, it will change the orbit, and that would be super easy. Even in such a low resolution scenario, it will be super easy, and we'll have an absolute confirmation that something happened. We dumped energy and we can get some actual data out of it. So we did that. Now this is the actual from this, as you can see, this is the main puppy, this is the moonlet, and probe is like, I got you fam, and we have missile targeting lock system, and then you boom, it did that. Like, and we actually got confirmation from our other satellite. Even James Webb Space Telescope have like a small splash where you can see it. It's like, oh, something happened. So this worked. Now this puppy was $320 million mission. Now from an Earth defense point of view, you would expect it to be much more expensive, but that's the idea. It's like, we do not want to rely on like, oh, something is actually coming towards us and we are hoping that we know what to do. This is like, okay, let's test it out. It's almost like how you crash test your car in order to figure out the airbags work or not. All right, crash testing and all that. That's how we know that things work. Same thing. We think we know, we have to test it. It did. And we did this, it worked. But here's a problem. We got it and the orbit changed, but data is still sloppy. Now this was just one part of a bigger plan. The original plan was very massive. It had every country working together, be it ESA, be it JAXA, be it all other players. The idea was, because again, we are talking about Earth defense. It's not like, asteroid, like we're not gonna just like, oh, asteroid is falling on China, who cares? No, it was like the idea was whole planetary defense. So everybody will contribute into it, because again, many times we could find ourselves in a scenario, it's like we need a rocket today, and you may have like, your assets pre-deployed. So that would be a very sticky situation. So we need worldwide system, and again, you need worldwide communication array and all that jazz. So this was just one part of it. Unfortunately, that program fell through, and this is like a remnants of that original grander program. That's why I'm talking about the budget. It's much smaller than what they were actually envisioning, and they had other players also. So this is DART mission. It happened, it worked. We just need to figure out more about it. So Hera is part 2 of that same idea. So this mission cost is 290 million euro. So this puppy is a bit more expensive. So this idea is that this puppy was launched in Falcon 9, 7 October 2024 recently, and is gonna reach Dynamis asteroid system in December 2026. Expect January. Now be mindful, this is not a guaranteed system, because there is a tiny probability that it may have way too much ejecta, that once you actually go there close by, you may figure out, hey, there is too much ejecta there, as like too many tiny rocks. Sending a craft through there is guaranteed a boom device. So we may expect some delay or something. That's why it's unknown. We do not know. We just did something, something happened. Right now, that's all we got. Like if this, then that. We do not have absolute variable here. So this is what we're gonna do, part 2, in order to figure things out, what actually happened. Now, the core technology here is like, there are a lot of technology, but one of the very core aspect is technological demonstration of autonomous low gravity orbiting. Meaning, if you're talking about something like, city killer or a country killer, small country killer, in those sort of scenario, the gravity there is there. It's not zero, but it's not so much where you can easily, oh, we know how to write a program to just like take a orbiter. It's not moon. It's not moon. It's a very small. So you need to be very slow. Like you need to be like almost like very slow. It's like, I got this. So that's a complex thing. And because of the distance, you can't command it. And there is no U-turn if you make a mistake. So it has to be autonomous. So that thing will be tested on this puppy. And it also has 2 extra CubeSats, because they do expect some mess there, that they're going to deploy 2 of the CubeSats and they're going to go closer in. And even if they get boomed, because be mindful, they were planned to actually go boom on it. So it's acceptable, so to say. But again, the mothership should not be in danger. And the idea is these CubeSats will relay data to the mothership will relay to us, basically using this high gain antenna. So this is the whole point of it. We did something, now we need to figure out what actually happened. Basically, it's like sniper went pew. Now somebody actually going there is like, okay, what happened? What is the penetration and all that? So this is the Hera mission, part 2. So what about the mission here? Well, mission is very simple. After launch, it should cross Mars, because be mindful, we are talking about Falcon 9. While Falcon 9 is very powerful when it comes to low Earth orbit, it's not that high energy. It needs a third stage. So without third stage, then you need to do a lot of what you call orbit raising maneuvers kind of scenario. It's like you have to increase the delta V using gravitational assistance of Mars. Now, why didn't they use any other rocket? Yeah, that's the core part that I have to keep talking about. It's cadence. Every company on paper have something that they can do use better than Falcon 9. It's just that none of them can actually deliver. It's like you pick up a phone, it's like, hey, ULA, bruh, I need a rocket. It's like, yeah, that will take at least 2 years. So that's and Ariane 6 is like, hey, yeah, that's gonna take 7 years. It's like, yeah, no, that's the whole point. That's why Falcon 9, even if you have to delay the mission, people just do it because, again, A, it's available, B, it's so cheap. So they're like, okay, now we're gonna do orbiter assistor. I'm just hoping someday somebody bitch slaps Elon Musk and he's like, okay, we get it. We're gonna put third stage in Starship. Then we can do ultra deep mission. Like we may be able to go to Pluto in instead of 10 years, maybe very quickly, or even better, go 10 years, but do orbiting, not just flyby. That would be awesome. So it's going to do gravitational assistance in March 2025. Then after that, is going to do rendezvous in December 2026. Now, again, rendezvous means it's going to utilize its thrusters to slow itself down. And after establishing stable orbit, only then it's going to deploy the CubeSat. And that's all unknown, because we do not know what is the local environment there. Because if ejecta is small enough, it will not reflect enough light for satellites to catch it. And only when you get close enough, it's like, oh, there is a debris cloud here. So it's a unknown. So be patient at this point in time. And both CubeSats were deployed. Now be my friend, you do understand this does require a lot of oomph. So this puppy has 16 orbital class thrusters and 6 reaction thruster. More than enough horsepower to gently do. It's like, I get this. At least we hope. So this is the mission. And this was a launch event. They deployed it. Now, what about the instruments? Well, instruments wise, they have a lot of cameras basically. So one instrument is asteroid framing cameras. Basically, you have to understand, they need very precise feedback loop in order to be damn sure that they can orbit it. So they have this camera, this puppy, and this has very weird resolution. It is like 1020. And I do not accept that to be a real resolution. I think its sensor is 1024 and they have 4 as a dark pixel. And again, it's a common thing to do. Many cameras, many or almost all cameras generally have some dark pixels. So you take the silicon, it actually has all those pixels. All of them are working. They just color it black. So the idea is that will be in your digital frame, the actual file that you get out of it. And using algorithms, you can extrapolate what is the electrical noise. Because again, there won't be any photon noise. So what is the electrical noise at the shot? That will be collected for noise reduction, and then you're gonna have better. So that's why I find it odd. 1020 does not make sense to me. Again, that's my interpretation, or maybe this is some weird camera that actually has 1020. So, but my money is it's 1024, and those are dark pixels, so to say. So monochromatic, again, they need very high precision. so monochromatic. And on top of that, it has a hyperspectral. So that puppy is monochromatic, and this puppy is like, I got you, fam. I'm gonna give you everything. Now be mindful, almost all cameras are black and white. So what you do is generally put 3 filters on it, red, blue, green filters, in order to get color image. Now this puppy is an upgraded version of that. What if you had a light coming through a slit, like only a 2D scanner line, basically exactly how your scanner works. That light goes through what we call a prism, so to say, or a Fresnel lens, so to say, and it spreads it out. And then you have a sensor. In that sensor, you have a basically gradient mask, so to say, and that gradient will only allow, like this pixels, if they are triggering, they are triggering for red. If these pixels are triggering, they are also triggering for yellow, only yellow. So you have a color, band pass filter, gradient band pass filter, sensor, and then you have a Fresnel lens, so to say. So diffraction grating, sorry, why I'm saying Fresnel, diffraction grating, and that's how you get it. Now, here's the deal, you will realize that only gives you a 2D data, it's like X and Y. There is no, like, Y as in like the depth, like, what is in what wavelength. So that's good, but again, it's not an image, it's a still 2D line. So to make it 3D, like voxel crate, like, what we call data cube, it uses the motion of the craft in order to do it, and that's how we do it in satellites. So hyperspectral camera, because again, this is the easiest way of doing it, so we just use the motion of the satellite in order to scan the whole thing. So that's what they're gonna do. And again, you can buy this if you have very deep pocket, but again, this is specifically new progression done for cube satellites, so you can do very small puppy and it can do really high resolution. This puppy is supposed to have around 24 slices from red to blue to ultraviolet, blue to basically infrared. Whole of the silicon spectrum, has a slice for it. So the precision, basically the voxel cube that's going to make, or the data cube, it is very rich. So black and white gives you the general idea for navigation. This puppy is like exactly what's happening. And because it has such a fine slices, it can tell you, okay, this is copper, this is iron, this is silica. So that's hyper. And how it's doing that? Push broom. Again, exactly. Look into your sensor. Flat bed scanner, exact same thing. Only instead there you are moving the sensor. Here the sensor is fixed. It's just using the motion of the craft, or maybe craft would rotate in order to do a sweeping motion. Many cameras do that. It's a common thing. So you have hyperspectral for that, and then you have thermal infrared imager, which again goes deeper into infrared, because again this also does light infrared, short wavelength infrared. But you want to go in deep, you do need different kind of sensor. So that instead of silicon sensor, you may have to go to gallium sensor. So that puppy is coming from Japan. Now that puppy should allow how the heck sun's light is affecting it, because we do expect one of the defense grid to be like, hey, what if we painted one side and it started to reflect more light, and how would that affect either thermally or just like photon bouncing. So you do need thermal feedback loop for that. So this puppy should give us a rough idea. It's like how thermals are behaving. And then you have PALT. This is laser rangefinder, this puppy. So laser goes yeet, and then comes back from here, twing, then goes through here. So that's there. And this should also allow for like a much finer resolution, where it's like, no, I'm saying this. Now this is just on the main puppy. The smaller puppies have a radar system, but these are the main critical elements, so to say. So why are we doing it? Right? Because here's the, without follow-up study, we do not know what the heck happened. We just know that we threw something, it hit something, something happened, something changed. So everything is just like, what if this, then that, like, that's why all our rendition before the mission actually gets there is like always wrong. We are just assuming, because again, what we have is pixel data on a radar telescope, or 1 or 2 pixels in a freaking telescope. So that's not enough. That's why, like, whenever we draw something, it's like, oh, this, and then satellite actually go there, oh, it's completely different. We do not know. So we do not know what the heck happened. Let that be very clear. We have idea, we have hopes, we have dreams, what happened, but we do not have precision. Basically, we are literally using old mobile phone which had a VGA camera. So it's like that. And evaluation of kinetic impactors evaluation, basically, does it actually work? Because we thought we can calculate, like, this was the puppy and we boomed it. What was the velocity? What was the mass? What was the velocity? That gives us how much joule this puppy had. So we went bam. How much was transferred? Now again, you know for a fact that 100% cannot be transferred, but how much was transferred? Is it 10%? Is it 20%? Because it can be anything from 0 to 100%. So we have to calculate it. And again, you may be like, can't we analyze by orbit? Orbit is a sloppy measurement. You need very high precision, because again, this sometime, hopefully when we are fully ready, we may have to use it. And again, it's almost guaranteed that we need to use it on some asteroid redirect mission. It's gonna happen. So you need precision. It's not like in science you have to understand. It's about all about prediction. If you can say this puppy is gonna happen, when it's gonna happen, within margin of error, then people are like, okay, now you know what you're talking about. So to know the margin of error, you have to do follow-up study. So evaluating kinetic impactors, method of deflecting kaboom devices. Basically, if big asteroids are like, today this city disappears, and then we like, no, go away, shoo. So we need to do that. And what do we actually need to figure out? We need to figure out momentum transfer. That's the essence of it. Basically, we did this, we got this part sorted. We have missile hitting algorithm, we got this. It's just like how much energy was transferred. How was it? Was it transferred all of it in ejecta? Was it transferred in actually changing the velocity? Did it deform the puppy? We are just running simulation at this point in time. Everything is just hopes and dreams at this point in time. So we need a follow-up study. Without that, we are just hopes and dreams. And that's why I like the idea of having 2 extra CubeSats, which actually gonna use a very high quality radar in order to tell, is this a clump of particle, or is it just like a big solid rock? What are the probability of it having larger rocks, smaller rocks? And again, hyperspectral will show what is the combination of surface details and surface textures, and thermal, like how sunlight is affecting it. All of those are important. Again, what if we found out like majority of this area became molten? Because again, you are talking about orbital velocity, you went verbatim into it without atmosphere. That may have some unique interaction. We do not know. So momentum transfer, without data analysis, we have just hopes and dreams. We need to do better. And without more data, we are not safe. Because again, I would like humanity to do this 10, 20 times. So it's like, if an asteroid finally is like, I have this city's name, NASA would be like, bruh, come on, man. We just had this mission. Okay, change this mission. Or maybe if we have world peace at that time, we will just like, Japan will like, hey, I have a spare rocket, man. Just don't worry about your mission. I got the spare rocket. And then, so because again, it's a high priority. It's like other country like Australia would be like, hey, I got you, fam. We have another rocket just in case, just in case, or a follow-up mission. If the primary fails, we got the follow-up just behind the ship. So that's the hope, that's the dream, that's what they are working together. The idea is we're supposed to have a whole toolkit in order to like, I got this. Because big ones, they require a different kind of toolkit. Small ones, they're goddamn hard to find. And again, how the heck we impact it? Because there is a probability of worst case scenario where you fire a projectile in a super high speed, again, orbital velocity, it just goes through it. Again, it has not happened yet, but there is a probability that that could happen. So we really need to know. That's why we have to transfer from hopes and dreams to like, this is what happened. So this was my presentation on this ESA as a part 2 mission. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.